Hello, it's Keith here, and this is lesson 59 of the platform-specific series of my 650 assembly programming tutorials. We look at Mintile, my multi-platform tilemap code, and we're looking at the NES today. Now the NES, of course, has a tilemap. It has a hardware tilemap, and so in some cases we'll just be transferring the tiles from the software tilemap source to the actual VRAM. Now there is a bit of a tricky thing though, because Mintile is designed to actually support XFlip, and the NES tilemap does not support XFlip. It's also limited to 256 source patterns for the tiles, and that's not really enough because the Chibico character is designed to have up to 128 on its own. So what I'm actually doing is when we turn our character around, you see here it's currently unflipped, but if I flip it around by pressing the fire button, there we go. It's now actually a hardware sprite, and you can tell because it's actually moving in individual pixels, and we're blacking out the parts of the tile map that it's under, that are under it, to actually mimic the same effect as the unflipped tiles. So there it's tiles again. There it's hardware sprites. The hardware sprites can XFlip, you see. Now, this is a bit of a weird solution, but it does have one benefit. The sprite patterns are 8x8 pixels that we're using here, and the Chibico character is actually using so many that if both the characters on screen were hardware sprites, we'd actually run out of hardware sprites. So we're not using them all. That is one of the tricky things about today's example. The other tricky thing, which I think will interest you if you're looking to use hardware sprites or tile map data, is the VRAM on the NES. We can't actually write to VRAM unless the screen's switched off or we're in VBlank. And so what this code is actually doing is it's building up a cache of data for the tilemap background and the hardware sprites, and then it's transferring that data during VBlank. So that's how it's getting around it, but that's not even the end of the complexity, you see. Unfortunately, because of the speed of the VBlank and the speed of transferring data, we can't transfer the full tilemap each time. This leaves us with two choices. The first choice is we just update a few of the tiles at specific locations. I've done that in some of my other examples, but that's not what I've done today. Here what we're doing is we're basically transferring one solid block of the tilemap each time. We're basically transferring a quarter of the tilemap in sequential order. So every 4 frames we would have updated the entire tilemap, and that's why you can see some screen tearing as we're moving around the screen, possibly depending on how the frame rate's recording there. But basically the reason I've done this today is this is the more flexible solution. If we're doing like a heavy scroll like that, an awful lot of the tilemap's probably going to change there, and so just updating 32 tiles per frame there is actually going to be worse off than trying to update as many as possible in sequential order, because writing data sequentially is faster than writing odd random VRAM destinations. So a lot of problems there that we're going to get around in our code. So let's go over and let's take a look. Okay, so here's our code here. Now what we're going to define is we're going to basically define a VDP buffer here. We're defining that at memory address 200 in memory here, and we're defining a sprite buffer. We're allocating 400 bytes in hexadecimal there for the VDP buffer for the tilemap, and then that's our sprite buffer, which is 256 bytes. Now the sprites, transferring those is actually easier. We have a DMA that transfers them all in one go in a single command, very fast. Shame we don't have that for the tilemap really, but we don't, so we can't use it because it doesn't exist. So that's what we're going to have to deal with. First of all, let's have a look at our NMI handler, the non-maskable interrupt handler. This is the stuff that actually does the job of transferring the data. Now, the nice simple thing is transferring the sprite buffer. Basically, we just write a byte to port 4014, that's a memory mapped VDP port, and this is actually going to start the DMA, and all we do is we write the high byte of the memory address that contains the sprite buffer, and it will just transfer it all in one go. And so we do that at the very last stage of our interrupt handler. At the start of our interrupt handler, basically what we're doing here is we are basically checking to see if VDP update is 0, because maybe we've not written anything to VRAM yet, and so we wouldn't update anything in that case. But if we have written something to VRAM, we're going to force an update and we're going to transfer some of the data. So what we're doing here is we're loading the HL pair of the current position in our cache that we actually want to write to. Now we're writing to what's known as the name table in VRAM, which is actually the tile map. It's the map of 1 byte tile patterns that we want to show. So that's at memory address 2000 in VRAM. It's at memory address 200 in RAM. So that's why we've got this calculation here to calculate the correct offset to the actual VRAM destination that we want to write to. And then we've got a partially unwrapped loop here, and what we're doing here is we are repeatedly reading in bytes from the VDP cache in RAM and writing them to port 2007, which is the port to write data to VRAM here. And so we're doing that repeatedly. We're doing B0 bytes in hexadecimal. That's as many as we can transfer, roughly speaking, within one VBlank. You might be able to get 1 or 2 bytes extra, but that's a nice round number to work with. So once we've done B0 bytes, that's basically all the time we have. So at that point, we're going to give up. What we're then going to do is we're going to reset the scroll position. You see, every time we write VRAM, the scroll position changes, which is why we can't really write to it at any time other than VBlank. So that's resetting the scroll position. We're updating a VBlank flag, which is for some of the old code. That's basically a flag that we can use to detect if VBlank has just occurred in our main code. And then what we're doing here is we're updating the L part of the VDP write position. So this is remembering how much data we transferred this time and so we know what to start transferring from next time. So we're updating the L part, and we're updating the H part here, and then we're comparing the H part to 0.5. Now, if it's below 0.5, then we've not finished writing an entire buffer, but if we've gone over that, we've actually transferred the entire VRAM buffer into VRAM, and we basically need to reset back to 0. So what we're going to do there is we're going to update the HL pair. We're writing 40 to the L part here, and this is effectively skipping the first 2 lines. So we're limiting to just to the center part of our screen here. That's so because we really don't want to write any more than we absolutely have to because of the limitations of speed here. So we're skipping those 2 lines there. And then we're setting the H part back to 0.2, and we're writing the value of 0.2 here to the VDP update value here, and that will make it so that when we get here next time, we will actually skip over and not write anything, and so we will need to write a value of 0 to this to actually force an update next time, and you'll see that in the code. So that's the interrupt handler that's doing the dirty work of updating VRAM. So once we've done that, we can now just worry about doing everything in the cache. So I think we'll have a nicer time of things now, I think. Okay, so that's what we're doing there. And so now what we're going to do next is we're actually going to define the tiles. So we've looked at this kind of code before, so we'll just quickly look at it again. So all this is going to do is basically transfer the source pattern data from our cartridge into VRAM. And so what we're doing first is we're disabling the screen, and that is the other way to safely get to VRAM, turn the screen off. Okay, at the start of our game, not so good in mid-game, so that's why we're using the simple option here, not during the actual game. We're then using this prepare VRAM function. We'll find that. Where is it? So all this is doing is writing the DE pair, that's a pair in the 0 page, to port 2006. That is selecting the actual VRAM destination that we're going to write to. And then all we need to do is basically we're loading our Y register with 0, and we're loading X with the C part of the BC pair, that's the byte count, and we're transferring a byte from the HL source in the 0 page to the VDP destination here. We're incrementing Y. Once Y has basically reached 0, we're incrementing the H part of the HL pair. That's moving to the next 16-bit part of the data. We're then basically checking the X register here. If the X register has reached 0, then we need to basically decrement our B part here. We're basically using the X part as the low part of the BC pair here. Just a little bit faster there. And that is transferring our pattern data into VRAM. So that's how we've got our patterns. Now, when it comes to drawing our background tilemap and our sprites, we've got our tilemap here. This is our tilemap background, and this is our Chibico character, that little mascot there. It's a miniature tilemap, if you will. And the way Mintile actually works is it actually draws tilemaps to the screen. Now, we've got 2 ways of calculating our VRAM destination. If we're drawing the entire screen, we use this screen base value here. If we are drawing to an irregular location, drawing the miniature simulated sprites, we use this get screen pos function here. Basically, all we're needing to do is calculate the VRAM destination in tiles. We are converting the X position to a tile number, the Y position to a tile number, effectively multiplying the Y position by 32, adding the X position, and adding the top byte of the VDP buffer address. So we're calculating the position in the VDP buffer. We never write to VRAM. Now, when it comes to drawing a tile map, whether it's the entire screen or just a little sprite, we're going to break it up into strips. The Mintile code is mostly multi-platform code, and so what it does is the multi-platform code does the dirty work of calculating the tile map and the cropping and things, and then it passes as little as possible to the platform-specific code. The less the platform-specific code has to do, the less we have to write every time we port this to a new system. So all we're getting the platform-specific code to do is draw just one single strip to the screen. So we start from the left, draw the tiles to the screen, move down the line and draw the tiles to the screen and repeat until we've drawn our tile map or our sprite. That's what we're doing. Okay, so how does this work? Well, the tile map contains a single byte per tile, and the value of 0 has a special function. Basically, in the case of the background, the tile map is actually a cache of changes, so a 0 in there means that nothing needs to be done. In the case of the sprite, it's a transparent area like around the feet of the character where basically there's no tile in that position. So what we're doing here is we're loading in the tile from the BCS 0 page pair. That's 2 bytes, the address of the tile map. And if that's a 0, we're skipping this tile. Otherwise, we're storing the tile number for a little later. We're then loading in the tile clear flag. This will be a 1 if we want to clear the tile map. So in that case, we're transferring X to the accumulator. X is 0 throughout this entire routine. So we're basically writing a 0 into the tile map there. Now, if we've got a tile number that we actually want to show, we're basically adding the ES entry in the 0 page. That is actually an offset, so if we wanted to start from tile 128, then we could set ES to 128 here. It's useful in some cases, and so we're then storing the tile number into the HL entry in the 0 page, which is the destination in the VRAM cache there. We're then incrementing our VRAM destination, increasing our tile map position in RAM, and then we're decreasing the count of tiles per line, and that's how we're doing the unflipped tiles. Now the reversed tiles are a little bit trickier. So once again, we're loading in our tile number and we are zeroing the entry in the tile map if required, but then we actually we're basically going to work with the hardware sprites. Now we have the next sprite number in VDP next sprite, so this is actually the offset within the sprite cache. So there was 4 bytes per sprite, and so this is being loaded into Y here. And what we're going to use is we're going to use the BC coordinates here. There's the C and the B. We loaded here and we stored in D. And we're shifting these to the left because these are the coordinates in Mintile are in logical units, and 1 logical unit is 2 pixels. So we're converting these to pixels here. We're adding 8 because the top 8 pixels are actually off the visible screen here, so we're just compensating for that. And then what we're doing here is we're setting the Y position here. We're incrementing Y. We're then setting the tile number here. We're then incrementing Y. We're setting the flags here, and we're setting the X flip flag here. That's the whole reason we're using hardware sprites in this case, and we're storing that, incrementing Y. And then we're storing the X position, and we're incrementing Y. So we've written 4 bytes there, and that has defined a single sprite. Now what we're doing next is we are writing a 0 into the matching entry in the tile map. We're still using the tile map, and that is so that when our character is X flipped, we still are removing the background to get a similar effect to the actual tile map data. You can see the black area is not moving with the same synchronicity as the sprites because the sprites can move in pixels and the tile map cannot. So what we could do if we wanted, and what this code originally did, is it was actually clearing the bottom 3 bits of the X and Y coordinate here, and that would limit the hardware sprite movement to 8 pixel blocks, and then it would match the tile map position. But I thought that smoother movement was a better example, so that's what we've done. Anyway, once we've done this, we're basically moving the X position across 4 logical units. We're moving the Y position down 4 logical units here as well. And we're moving to the next tilemap VRAM destination. And we're moving to the next source position in the tilemap. But we're decrementing that because we're moving from right to left in the tilemap because the tilemap has been X flipped. So that's what we're doing there. So that would be the case of this. This is the sprite tilemap. So we would start here and we would go from right to left if we are X flipped. Now that's how we're drawing our sprites to the screen, but there's one last thing we need to do. So before we draw our sprites, we need to draw our sprites every single frame here. And before we start drawing, we need to set the VDP next sprite to 0. We need to reset the number of sprites we're using every time. And once we've drawn our sprites, we need to clear any unused ones, and that's what we're doing here. Now, if we didn't do that, if we just disable the clearing code to remove the unused sprites, and we run our example again, Well, at first everything seems just hunky-dory. If I just flip my sprite there. So everything's fine so far, but then if I start moving off the screen, you can see we've got this weird trail of bits of feet. Why have we got that? Well, the sprites are still on screen and they're not being given anything to do anymore. And so until our character comes back on the screen, they will just linger around. And that's why we have that code to remove any unused sprites, basically working from the last VDP Next sprite that was used and continuing until it reaches 256 here, until it loops around back to 0 basically. And that is clearing the unused sprites, and that stops that clutter from happening. If we put that code back in and we do that again, so here is our example, and once again we flip our character around and we move the sprites off the screen. They've all gone because we gave them a position so that they were not being drawn. That's what we did there. That's how we get around that. Anyway, that's all we've got to cover today. I hope you've enjoyed what you've seen. We're going to be looking at a more advanced Tilemap example in the future called Max Tile, which does Y flip and a few other effects and hopefully makes more use of hardware sprites. So if you want to see that, please stick around. Anyway, hope you've enjoyed what you've seen today. Thanks for watching and goodbye.